Hello everyone, it's a pleasure to talk about more on variance of fatigue damage in non-Gaussian random loadings effect of skewness and kurtosis. My name is Julian Marcel and Marques. I am PhD student in engineering science at the University of Ferrara. I will start with a simple example. Assuming a bicycle excited by road irregularity, the measurement provides a random time history. Its estimated fatigue damage is computed. The second measured time history record is obtained from the same bicycle, same process. The third one is obtained again and so on. The fatigue damage changes slightly. It is affected by statistical variability, variance of fatigue damage. In this example, random loadings follow a Gaussian distribution. Several theoretical models were developed for the variance of fatigue damage due to Gaussian loadings. However, they do not apply to loadings that are not Gaussian, most practical applications. For example, wind and wave loads. The non-Gaussian loadings are characterized by kurtosis and skewness parameters. The goal of this work is to assess the variance of fatigue damage taking into account the non-Gaussian effects, kurtosis and skewness of loading. This is the outline of my presentation. I will start with literature review, being more specifically, general formulation and analytical methods for Gaussian loading. Then I will show the proposed method for non-Gaussian loading. I will deliver a few results using a simple numerical case. Finally, I will point out conclusions. To begin with literature review. Fatigue damage can be computed through time or frequency domain approach. Time domain is based on well-established procedures, rainflow counting method and palm green minor rule, so that the accumulated damage during an interval is defined as a linear summation over all damage half cycles. Note that it depends on a particular time history. On the other hand, we can use frequency domain approach to compute the expected damage. It has the possibility to obtain all statistical parameters through frequency spectrum, power spectral density, PSD. The expected damage using those parameters represents the whole ensemble of realizations, infinite time histories with infinite time length. The expected damage is then the mean value of the damage distribution. The accumulated damage during an interval from 0 to time t is used to define the variance of damage distribution. The variance is formulated considering the damage half cycles a random variable. The general formulation is equal to the expected double summation minus the square of expected single summation. It is often normalized to expected damage, which results in a so-called coefficient of variation. Under a few assumptions, Marques and Crandall proposed the first analytical method to estimate coefficient of variation. Bennett developed a more general expression for the coefficient of variation. Both methods date back to 60. More recently, Lowe developed a method applied to any narrowband PSD. However, these methods, Marques and Crandall, Bennett, and Lowe, are analytical methods for Gaussian random loadings only. Regarding to the proposed method for non-Gaussian loading. The Gaussian random loading is linked to non-Gaussian through nonlinear transformation. A few authors provide the analytical expression of this transformation. However, only the Winterstein's model provides the expression of direct and inverse transformation. The inverse transformation is a great advantage compared to other transform models. The model is based on Hermite polynomials and applied to a wide range of skewness and kurtosis. We can observe that the coefficient of variation and variance depend on the joint peak-valley PDF, which is the key element to compute the variance. The non-Gaussian joint peak-valley PDF is derived based on the Gaussian, known, and transform random variables. Note that the peak and valley in non-Gaussian are transformed back to correspond peak and valley in Gaussian through the inverse function. The general expression of non-Gaussian joint PDF is finally obtained. We compared the Gaussian and non-Gaussian joint PDF. The non-Gaussian is plotted with kurtosis 5 and skewness 0. The shift of probabilities is clear. The non-Gaussian shows higher levels of probability for larger peaks. On the right, we can see that such levels tend to increase when the kurtosis parameters increases. Regarding to numerical case study, the target PSD comes from a narrowband rectangular shape. The main frequency is 10 Hz. Analytical methods, Lowe's method, and proposed one are used to compute the Gaussian and non-Gaussian expected damage and variance. A large sample of time histories is simulated from target PSD. For every simulated Gaussian time history, the Winterstein model is used to transform into non-Gaussian. The fatigue damage was calculated in time domain for both Gaussian and non-Gaussian. The sample mean, variance, and coefficient of variation were estimated for Gaussian and non-Gaussian too. The theoretical methods were verified by Monte Carlo simulations. We can see the mean and standard deviation normalized to the expected damage over number of cycles. The results comes from Monte Carlo simulations in time domain. The lower is the number of cycles, the greater is the dispersion around the mean of damage. For kurtosis 5 and any number of cycles, the non-Gaussian always has a variance higher than Gaussian, about 100%. These results confirm that the non-Gaussian effects must be taken into account. Now the coefficient of variation for inverse slope of SN curve 3 is plotted versus the number of cycles. A perfect matching is observed between the proposed approach and time domain simulations in Gaussian case. A perfect agreement between the proposed approach and time domain simulations is obtained in non-Gaussian, kurtosis 8 and skewness 0.5. The same is observed in non-Gaussian with kurtosis 2 and skewness 0.2. The ratio between non-Gaussian and Gaussian coefficient of variation shows the effect of kurtosis and inverse slope of SN curve. Kurtosis lower than 3, the non-Gaussian has a lower variation compared to Gaussian. On the other side, in the region of kurtosis greater than 3, it always shows a larger variation. It is also clear that the ratio depends on the inverse slope. For example, for kurtosis 5, the ratio increases about 2 times for inverse slope 3, while it is 8 times for inverse slope 7. This confirms the meaning of taking into account non-Gaussian on variance of fatigue damage. Finally, I will let important conclusions. A method to assess the variance of fatigue damage in non-Gaussian loadings is introduced. A transform model is the link between Gaussian and non-Gaussian variance. The proposed approach is very accurate and covers any combination of skewness and kurtosis of practical interest. Gaussian models leads to unsafe variance of fatigue damage, especially for high kurtosis and inverse slope, SN curve. Thank you very much for your attention.